it is time for our revision. So we have learned quite a few predictive models. What are the how can we classify them? Okay, so we'll follow the mathematical approach. Okay, that is how are the predictive models being constructed mathematically. Okay, to actually classify the predictive models we have learned. Okay, so the first type, or the first class of predictive models are the so-called discriminative approach predictive models. Okay, so these models are basically performing prediction based on the boundary, okay, of the response variable. And the other type, okay, the so-called generative approach predictive models based on learning the distributions of the individual response. Okay, so we'll first give some examples of the discriminative approach. Okay, these are some of the discriminative approach models. Okay, KNN, K nearest neighbor. So based on what we mentioned just now, okay, if you remember how this thing is calculated, it's actually calculated based on the data. Okay, we give in the new data. Okay, using the old data, we try to find who are the closest to it. Okay, the K closest to it, and determine the response. Okay, the type of response. Okay, let's say it's a binary response, so it's either 0 or 1. So if K equals to 3, so if we have 2 1s and 1 0, okay, then the probability of getting 1s would be higher. Okay, so we will determine for the new data, okay, to be 1. Okay, so this is KNN. And if you look back into your lectures, you can see for the two-dimensional case, it's very easy to understand. Okay, it's just some positive classes, negative classes. Okay, in between them there seems to be something like a boundary. Okay, and depending on your K, maybe if you choose 1, okay, you can draw a boundary, and you'll find that okay, then we can basically on a two-dimensional plane split out the so-called positive classes and then negative classes. Okay, so the determination, okay, of the classes of a discriminative model is basically based on the boundary. Okay, whether it's possible for us to visualize or not. Okay, it's based on boundary. Okay, so logistic regression is also a kind of discriminative model. Okay, so where does the boundary come from? It comes from equating the output to 0.5. Okay, normally we say above 0.5, we say it's positive class. Below 0.5, it's going to be a negative class. Okay, so so the part which we can't actually determine whether it's positive or negative, or okay, it's up to us to whether to put it positive or negative is the value 0.5. So equating this thing to be 0.5, we can solve the equation, and in the end we will actually get a linear equation. So it's something like a linear okay, in two-dimensional case, it's something like a line separating out the positive and negative class. So that's why it belongs to a discriminative model. Okay, tree-based model, because we directly just check the data, so just based on the data itself, okay, we determine it's y. So that's why just purely based on the data, okay, and we just purely based on this, and we can decide what should the output be. Okay, then it's a discriminative model. Okay, and lastly would be a support vector machine. Okay, it uses something called hyperplane to actually split out the positive and negative data. Okay, but it's not covered in our course. Okay, next class are the so-called generative models. Okay, why is it called generative? It's because instead of just taking the features, okay, and then try to predict what's the outcome, okay, we use the Bayesian theorem, okay, to transform this thing, okay, into the conditional probability part, okay, by exchanging these two parts, okay, and then multiply with the prior distribution. Okay, normally in this kind of approach, we actually have the output class of the data, okay, the class of the response. Okay, so we would actually have the prior distribution, okay, and then we just use the Bayes theorem, and then okay, so the key thing is actually to estimate the conditional probability. Okay, prior distribution normally is not something difficult to estimate. Okay, so let's see how this thing are estimated. Okay, as I mentioned, prior distribution, okay, many of you have seen this in naive Bayes. Okay, so it's basically just counting. Okay, so let's say you're training data as 100 rows. Okay, so for the output, right, okay, if we have only three classes, one is 20, the other is 30, the other is 50. Okay, so yeah, it's in the end we just have 0 0.2, 0 0.3, and 0 0.5. Okay, very easy to estimate. So posterior distribution, okay, once we have the estimate for the prior distribution, okay, we only need to have the estimate for the conditional probability, then we can actually obtain the posterior distribution, okay, just by okay, multiplication, and then divide over the sum of all possible response. Okay, so estimation of conditional probability, okay, you have seen this in linear discriminant analysis. Okay, it's using the multinomial I'm sorry, it should be multivariate normal distribution. Okay, so it's generalization of the one-dimensional normal distribution. Okay, and for naive Bayes, it just assumes that all the input features are independent, okay, probabilistically independent. Okay, so that it's possible for us to just split it out. Okay, of course, everyone knows from statistics that in general this thing is not true. Okay, so this kind of assumption, okay, for easy calculation. Okay, so just now our classifications are based on mathematical derivation. Okay, if we look at the parameters of the models, okay, we can classify the predictive models into parametric models, and also non-parametric models. Okay, so what are so-called parametric models? Examples like linear regression is a parametric model. Okay, because we actually have all the betas. Okay. Logistic regression also have all the betas, and linear discriminant analysis also have all this average mean, okay, the covariance matrix. Naive Bayes are all the priors and conditional probabilities. SVM we haven't touched on. Okay, all these have parameters in it, which are, okay, the key thing we have to remember for parametric models are the parameters are fixed. Okay, even the now very popular neural network, okay, they also have a lot of parameters in the model, okay, which are fixed. So it's something that based on the training data, we have to try to update the parameters. Okay, so the so-called non-parametric models doesn't mean that in the model they don't have numbers in it. Okay, it's just the data. Okay, it's more or less part of the parameter. Okay, so what does that mean? Means that as we give it more training data, okay, then the model will have more values in the model. Okay, so suddenly the data is the parameter, and normally we call these kind of models non-parametric models. Okay, the typical example is the KNN model. Okay, because basically we just put in the training data, okay, into the model, okay, and when we have new data, we just compare with the training data, okay, to see which rows are the closest to it, okay, and then based on the majority, okay, that will be the output class, which is for the prediction. Okay, for tree-based models, it's also a similar case. Okay, so the more data we provide to a tree, we know that it grows to be very deep. Okay, so the problem with this is then it's going to be inefficient. That's why in the end we need some kind of pruning, okay, to reduce the size of the tree. Okay, so the classification based on parameters previously is mathematical derivation. Okay, so next is okay, the mathematical derivation mentioned one of the approach, okay, which is separating based on boundary. Okay, so when we have some things related to the boundary, then we can define models which are so-called linear and non-linear. Okay, and linear class. Okay, so those which classifies positive or negative based on just a line or hyperplane. Okay, we call them linear classifiers. Okay, logistic regression. Okay, basically I mentioned it's a line or hyperplane. Okay, so it's a type of linear classifier. Okay, LDA, despite it's a generative model. Okay, when we actually perform the classification of data, we find that it also splits the data just using a hyperplane, so it's also a type of linear classifier. Okay, similarly, naive Bayes, okay, is mathematically, okay, we can derive it to be related to logistic regression. Okay, so it's also kind of linear classifier. Okay, of course, SVM is a typical linear classifier. Okay, so what are the so-called non-linear classifiers? Okay, just now we mentioned KNN having non-linear boundaries. Okay, so it's a kind of non-linear classifier. Okay, tree-based approach. Okay, if you recall segmentation of um, the data, okay, the data with positive and negative, right? Okay, the segmentation is in tree-based models, the simple trees, okay, it's normally just horizontal lines or vertical lines. So basically we cut them by something like square, okay, and then continue cutting it. So yeah, it's non-linear in the end. Okay, kernel SVM, kind of generalization of SVM, okay, to the non-linear case. And of course, the most famous nonlinear classifier and most powerful is the neural network. Okay, so let's take a look at how and why we have to talk about linear classifiers and nonlinear classifiers. Okay, so let's say we have this type of data, okay, on one side, okay, the negative, and here the positive on the right hand side. Okay, and we can more or less see that we can draw a line to separate this data. Okay, and accuracy would be very high. Okay, only some minor wrong prediction, okay, over here. So then for this type of data, the linear classifiers would work very well. Okay, however, there are situations where the data looks like this, okay, where the positive data are surrounding the negative data. So is it possible to construct linear classifiers? Okay, example is given from this slide. Okay, so it's still possible. Okay, we can construct a line. Okay, just to try to cut it out. Okay, but we will find that okay, so there are some data over here which will not be able to predict well. Okay, if we can construct something non-linear, like say we construct a circle over here, okay, to include those within the circle are negative and those outside the circle are positive, then we can have extremely high prediction accuracy. Okay, so these are the various ways of classifying predictive models. Okay, so it very much depends on the type of data we are dealing with. So next, we need to talk about the evaluation of predictive models. Okay, because having all the models, okay, which one of them is the best for us? So when we want to evaluate, we need to find what do we mean by how good is a predictive model. Okay, so most of us, okay, would probably start off with the default, okay, performance measurements, okay, accuracy, recalls, precisions. Okay, and many of us is wondering, why do we need to split the data into two groups, the training data and the testing data. Okay, so measuring good. How come we cannot measure good by just having the all data as the training data? Okay, especially for linear regression. Okay, normally we just feed the model, and then next we just find the regression error. Okay, can we not do this for classification? Well, the main problem is unlike regression, where we actually have a regression error to see how well it's fitting. Okay, classification problems are in general a bit something like nonlinear. Okay, so if let's say we have nearly zero classification errors, okay, how do we know that it's not overfitting? What do we mean by overfitting? Okay, overfitting, I would treat it as something like okay, memorizing. Okay, so overfitting, we can thought of it as something like memorizing. Okay, because this is a very important question from artificial intelligence. Okay, how can you differentiate a person, okay, from memorizing or understanding? Okay, so normally we use so-called exams to test if a person actually understands something. But the problem is, how do we set the exam question in order to actually know whether a person actually understands or actually is very good in memorizing? Okay, if we take the question from the textbook, then there is a tendency of some students who has really good memory would be able to answer everything correctly. But if a person actually just recites, okay, after a while he or she would not be able to apply, okay, to a situation which is similar but which the thing does not come out in textbook. Okay, so when we just purely use the classification error as a good measurement, then we will not be able to identify the situation of be able to distinguish between memorizing and understanding. Okay, and in AI, okay, so understands, we say a model actually more or less understand a situation. Okay, they call it a generalization. Okay, generalization meaning it can handle scenarios. Okay, the data which it has not seen in the old data. Okay, the so-called training data. Okay, and be able to provide a good prediction. Okay, that's why we want to have some kind of testing data set, okay, so that the classifier is not just memorizing but is able to predict situations which it has not seen in the training. Okay, so if we continue, we would ask the next question. Okay, so we say we need to split the data into the training and the testing part. Okay, so how many ways can we actually use, how many ways can we split the data in order to check Okay, remember we are trying to check how good is our predictive model, right? Okay, so the simplest is always just to split into the training and testing, but how many percent okay, we can just split something like 70-30, 75 25, etc., depending on how many data we have. Okay, if we have very few data, most probably setting something like 70-30 is a bit not nice, because the model may need more data to train it properly. So in that case, we might have to go to something like 90-10, okay, where 90% of the data are used for training. Okay, so what is the problem of this type of approach? Okay, the problem of this type of approach is that our accuracy, okay, actually depends on how we sample the data. Okay, assuming it's not time series data, okay, it's any data would do. Okay, so why are we taking the first 70 and not the last 70? Okay, and it's just like the data with 100 of them. Okay, either taking the first 70 or the last 70 is not really reasonable, right? Okay, why don't we just simply sample? Okay, whenever we sample, okay, we after taking the sample of 70, okay, the remaining 30 will be used for testing, and we actually performs prediction using the training data. Okay, every time we have different testing data and different models for prediction, we will get different accuracies. Okay, so all these accuracies actually would be somewhat different. Okay, so how confident can we be with this kind of accuracy? Okay, so in statistics, the proposed approach is to actually perform a k-fold cross validation. Okay, that is we just subcategorize the data into equal k parts. Okay, and then take the first k minus 1, okay, as the training, and the last one as the testing, and then we start rotating. Okay, like just now the last one is the testing data set. Okay, now we move to the first one as testing data set, and then the rest would be the training data set. Okay, so we just go through a k-fold. So for, let's say we have 10 of 10-fold. Okay, so we have 10 average accuracy. So we have 10 accuracies, and then we can just average them. Okay, so then the accuracy we obtain, okay, we would say that we have more confidence. Okay, it's just not based on one sample train test. Okay, so okay, this approach gives us more confidence. Okay, what we need to be aware is it still depends on the sampling. Okay, because how we cut into 10 into k partitions, okay, depends on what's the original order of the data. Okay, if we reshuffle, okay, and then cut into k folds, and all these would give us different accuracy, but statistically, okay, statisticians have actually checked, okay, the situation, and basically, okay, it's doing fine. Okay, the careful validation give us good enough confidence. Okay, so we have models, we have ways to measure them. Okay, so after measurement, the next thing we need to do is actually to select them. Okay, so we have talked about the performance measurements. Okay, and in the assignment, okay, many of you have actually just purely based on accuracy. Okay, some include more on also the recall and precision. Okay, to decide what model to choose. Okay, but many of you have forgotten that okay, models doesn't just give us decision. Okay, a lot of times, especially in management, we need to explain to people. Okay, so explanation requires sort of like an understanding of the model. If the model is too complex, okay, something like random forest, then it's a bit difficult to explain how random forests work. But for a decision tree, okay, if it's able to make a good prediction, okay, then normally we will try to use something like decision tree, because it's not difficult to explain a decision tree. Okay, it's because it's derived from the data frame itself. Okay, so from the data, we can actually see that, okay, some of the variables are more important. Okay, so so the decision tree would put the most important feature, okay, on the root of the tree. Okay, and then start go down, and the less important ones might be down there. Okay, something like that. Okay, and I believe many of you also are extremely familiar with the logistic regression. Okay, based on the p-value. Okay, a lot of you decide that, okay, this feature is not important. Okay, why is it not important? Because statistically, if the p-value is larger than 0.05, meaning that its contribution to the prediction of the response is not statistically significant. Okay, that's why we actually throw away the feature. Okay, and then just select certain features, okay, for prediction. Okay, then based on that, we can explain to people, okay, how this thing actually works. Okay, I think the other things which in real world situation we have to be aware of is, okay, what about the updating the model? Okay, first, as we collect more and more data, okay, so let's say after 2 years we have new data coming in. So the model has been used for 2 years, and we need to update the model. Are we going to retrain it? Okay, what about the even because the model is trained using older data? Okay, what about the older data? Okay, should we discard it? Okay, so this kind of problems. So updating is also something we need to be concerned of, and of course, okay, can we include the model into data processing pipelines? A lot of times we may need to be deal with data processing software. Okay, so when we want to include into the data processing software, okay, how to do it. Okay, so that's all for the first part of the revision.